Hello, class. On this video, we're going to start on section 2.7. Okay, so we've done a little bit of jumping. We went from section, let's see, we did 2.4, then I think we did 2.6, 2.6, and we went to 2.1, and we did 2.5, right? That was the face portrait section. Then we went to 1.1 doing direction fields, and now we're in section 2.7 in the book. So sorry about the jumping, but again, I think I explained in previous videos why I think that this order makes more sense. So if you want to follow, we are in chapter 2, section 7 in the book. So I've mentioned a lot of times already in these lectures that in the real world, a lot of the differential equations that arise from different systems we're trying to model are not actually solvable using analytic techniques. And when I say analytic techniques, it's just basically what we've been doing, where we can find an exact solution for the differential equation. So I mentioned that a lot of times you either just use techniques like direction fields or face portraits to get information about the solutions, or you have to approximate solutions. Most of the time, you're going to be approximating solutions. That doesn't mean that there is no analytical techniques in approximating solutions. A lot of the setup of how these algorithms work depend a lot on things that you learn in calculus or things that you learn in linear algebra. So there is some sort of analysis there, but in terms of the algorithm that we define, it's not something that gives you an exact solution, but just an approximation. And we'll see our first example of that in this section. Okay, so let's start. We're just going to consider this first order initial value problem. We have y prime equals 0.1 times the square root of y plus 0.4 x squared, and we want to find a solution that goes through the point 2, 4. Now, notice that if we started and we wanted to solve this differential equation with the techniques that we have, well, there's a couple things we can do. You can check that this differential equation is not separable, right? It's not exact, and it's not linear. Right? You can immediately see that it's not linear because you have the square root of y here. Right? So you have a power of a derivative of y. Remember that you can write y as its zeroth derivative. So you have a power of a derivative. That's one of the things that I mentioned, that as soon as you see that, that means that the differential equation is not linear. Okay? So that takes care of the three techniques that we have. We can either deal with a separable, exact, or first order linear differential equations. Okay? So in terms of the exact techniques that we have to get exact solutions, none of them are going to work. So what can we do? First, if you were doing this in the real world and you looked at something like this, the first thing you would want to ask yourself before you start even trying to attempt to find a method of finding an approximation to the solution is say, well, does a solution even exist? Right? And that's something that I mentioned when we were going over section 2.4, where we were talking about the existence and uniqueness theorems. Right? There's no reason in trying to approximate a solution to this first order initial value problem if such a solution does not even exist. Right? So it's an example of something you would do in the real world. Let's say this comes from some system that you're trying to model. Right? You want to find a solution. Well, none of the techniques that you have work. So before you start to try and approximate, first ask yourself, does this initial value problem have a solution? And of course, you can also ask, is it unique or not? So how do we answer this first question? Well, we can go back to section 2.4. Right? We had a theorem for this. What was the theorem? Just a reminder. Right? Given a differential equation, y prime equals a function of xy, and the initial condition, y of x naught equals y naught, when are you guaranteed that a solution exists? Well, you have to find an interval, and let me erase this so I can underline again. So let me get rid of all of this. So you have to find an interval about x that contains x naught, and an interval about y that contains the y naught, or the y coordinate of the point. And what you have to do, you have to check that both the function, right, so whatever expression you have in terms of x, y, and the partial derivative with respect to y of that expression are continuous on this region, given by, or which you can see here at the picture. You have this square, AB in the x-axis and CD on the y-axis. As long as that is true, you're guaranteed a subinterval. You don't know what the subinterval is, right? So that's why it was a little bit more complicated. But you're guaranteed a subinterval, let's call it I naught, in which you know that a solution exists to this initial value problem. Okay. So let's apply this to our problem here. Right? In this case, it's already in the right form, right? We have y prime by itself. So this thing here will be our f of xy. So what's the first thing we want to do? We know what f of xy is. So I'm just going to write it here again. This is 0.1 y to the 1/2 plus 0.4 x squared. And again, we have the initial condition, y of 2 equals 4. If you remember what we did in section 2.4, we need to work with f and the partial derivative of f with respect to y. So let's find that first. Remember, the way you do this is you take the derivative as you would with respect to y, treating any x as a constant, okay? So if we do that, the derivative of this with respect to y, we'll just bring 1/2 down, right? And then subtract 1 from the exponent. So that would be, so 0.1 is 1/10, so that would be 1/20, y to the negative 1/2. Now the derivative of this with respect to y, well, x is a constant for our purposes, so all of that is 0. Okay. So now we have our two functions, f of xy and the partial derivative of f with respect to y. What do we have to do? Find an interval about the x-axis and an interval about the y-axis where both of these functions are continuous. So let's do the work. Let's start with f of xy. So on what interval, so let's do it like this. On what x interval is f of xy continuous? And as I mentioned, continuity in 2 dimensions basically works almost the same as continuity in 1 dimension. There are subtle differences. You can approach a point about any direction. I won't talk a lot about that, but basically, if something is continuous in the 1 variable case, it's going to usually be continuous in the 2 variable case. And you check basically the same way. Are there any restrictions that I have here? Well, I have some restrictions on y in terms of f of xy because I have the square root of y. In terms of x, I can plug in anything for x here, which means for our purposes that whatever works in 1 dimension should work in 2 dimensions. In terms of the interval about the x-axis, we can take negative infinity to infinity. Right? We can plug in any x value. For y, it's going to be a little bit different, as I mentioned, because we have a square root. Should be an is, not an if. Well, as I mentioned, with respect to y, look at the expression that has y's here. The only problem is that we have a square root. As we know, the domain of the square root is positive numbers including 0, right? So non-negative numbers. So for y, we have to restrict to the interval 0 to infinity. That's for the function f of xy. Now let's look at the partial derivative. So for the partial derivative, somewhat x interval is partial f, partial y continuous. Well, there are no x's, meaning that x can be anything, right? So again, we can use the interval negative infinity to infinity. Now focusing on y, partial f, partial y continuous. Well, again, we have a square root, but now it's also on the denominator, right? Because remember that it's the same as 1 over 20 times 1 over y to the 1/2. So we already know that the domain of the square root is non-negative numbers. Now y also can't be 0, right? So actually, let me fix that here. Here, y could be 0. In this case, y can't be 0 because if y is 0, although we can evaluate the square root at 0, that would force us to divide by 0, right? Because we're dividing by y here to the 1/2. So here, we have to restrict to the smaller interval, 0 to infinity. Now, again, continuity is not as easy as this in most cases. You have to consider other things, but for now, since this is not a Calc 3 class, I can't assume you're taking Calc 3. We're just going to assume that it works on these intervals, okay? But in general, it's kind of hard to do it interval by interval. It's not how you would want to approach things. But in this case, we're just going to do it like this, just for the sake of the problem. So you need intervals on which both functions are continuous. That means that we have to use the interval, or the intervals, negative infinity to infinity for x, and for y, well, we have either 0 to infinity, including 0, or 0 to infinity, not including 0. Well, we have to pick the smallest one because it has to work for both functions, f, and the partial derivative of f with respect to y. So here we have to use negative infinity for x, and the smallest one, 0 to infinity for y. Now notice that this interval contains the x value of the initial condition, which is 2. Actually, let me just write it out completely. Notice that negative infinity to infinity contains x equals 2, and 0 to infinity, and I think this is 4, right, for y. Yeah. And 0 to infinity contains y equals 4. So, by theorem 2, in section 2.4, we're guaranteed that there is an interval about x equals 2 on which a solution exists. So, by theorem 2 in section 2.4, we are guaranteed that there exists an interval I naught centered at the input x value, so centered at x equals 2, right? Oops. For which the initial value problem has not only a solution, but a unique solution. Again, the problem with theorem 2, when we made it in the more general case where first order differential equation wasn't linear, is that we don't know what the interval is, right? In the case that our first order differential equation was linear, we can find the interval. Right? Now, if I were asking you to do something like this, right, outside of section 2.4, so maybe in the reading homework, I would want you to write something like this, right? So show the work, you show all the conditions required for theorem 2, and then you write a concluding sentence saying what it is that you showed. Now, this interval I naught has to always be included in the interval about that we found here for continuity about x, but since that interval is all real numbers, I don't have to rewrite that again. If this interval were smaller, let's say negative 3 to 3, then this interval I naught would have to be contained in that interval negative 3, 3. So it could be a smaller interval. Okay. So the reason why I go over all this, first, so you know how to use that theorem, so you see another example, but second, now we're guaranteed that there exists a solution, not only that, but exists a unique solution for this initial value problem. Why is that important? Well, now we can actually go and do the work of actually trying to find an algorithm to approximate the solution. Again, if no solution exists, there's no reason to approximate the solution because there is none. Now that we know that there is one, we can actually go through all the work of approximating it. So that's the idea, and this is an example of when you would use a theorem like this in real life. Okay. And again, these differential equations like this arise all the time, where you can't solve them exactly with the techniques that we use in class. So you have to do some sort of approximation. Okay. So in the next video, we're going to start on the algorithm that we're going to use to approximate what y is.